This is the second lecture from Chapter 4, and it is still concerning stoichiometry, but it is honing in on what we call limiting reactants in a chemical reaction. A limiting reactant is simply a reactant that runs out before other reactants. And the reason that a limiting reactant is important is because it's the limiting reactant that determines how much product can be made. Imagine that you're assembling something in a manufacturing line, let's just say bicycles. If wheels, tires, were your limiting reactant and they ran out, you would immediately not be able to make any more bicycles. Same thing with a limiting reactant in a chemical reaction. Once you run out of any of the reactants, product making stops, no matter how much of the other ones you may have in excess. The other concept we'll be talking about in this lecture is yield. Yield is simply how much product is made. And there are different types of yield that we'll talk about. I first want to introduce the idea of theoretical yield. The theoretical yield is the amount of product that could possibly be made if all of the reactants reacted. The actual yield, and that is what the chemist actually collects and weighs out. Okay, it's what the chemist makes. The actual yield is almost never equal to the theoretical yield. Okay, because, well, first of all, not all reactions go to completion, period. Some of them reach an equilibrium state and don't go any further. And there are almost always competing side reactions to a chemical reaction. And so the actual yield collected, honestly, from a bench chemist point of view, if you get an actual yield of 70% or higher, that is considered really, really good from a chemist point of view. So we've talked about theoretical yield, and that's the maximum amount that can be made if the reaction went 100% to completion, and the actual yield, which is what the chemist actually collects in the lab. And that depends on a lot of things, like how good the chemist is, what the conditions were, etc. The ratio of actual to theoretical gives, times 100, of course, gives you the percent yield. So we have learned about 3 types of yield: actual, theoretical, and percent. I would go ahead and write the formula down for percent yield. That's something you need to commit to memory. Here's a relatively simple example to get mainly the concept of yield across. In this case, we do have a limiting reactant, but it's not anything we have to work into our calculation. And that's because it makes it very clear what the excess reactant is. It says bromine is an excess. That means there's more than enough. And so what that tells you is the other reactant, the 6 grams of aluminum, is a limiting reactant, and so it is in fact the aluminum that's going to determine how much product is made. Okay, so as soon as that aluminum runs out, we will stop making aluminum bromide. So now you have to set up a T-chart. Your given information is the 6 grams of aluminum. So just a quick reminder, you want to go from grams of aluminum to moles of aluminum to moles of what they're asking about. And they are asking about aluminum bromide. To grams of aluminum bromide. 3-step calculation. What I'm getting ready to say is extremely important, so listen carefully and jot it down. The amount of product that you calculate, using stoichiometry is the theoretical yield. Okay? That's the theoretical yield, the amount that you calculate. The actual yield will always be given to you in the problem. Actual yield is not something you can calculate because every person, every chemist that goes into a lab and does this reaction will get a different actual yield, depending on the conditions the reactions run, maybe even depending on how careful or, well, the chemist set it up. So, in any case, the actual yield will always be given to you. So first we're going to go ahead and do our stoichiometry calculations like I outlined here, and that will give us the theoretical yield. Once you have the theoretical yield, you can use it and the actual yield to calculate percent yield. So there are 3 yields I've introduced here: theoretical, actual, and percent. Here are the stoichiometric calculations for the problem on the previous slide. I'm going to write it in a T-chart. If you are comfortable getting rid of the T-chart, feel free to. As long as you show your work, I don't care in what fashion you do it. But our given information is 6 grams of aluminum. The first step is to go from grams of aluminum to moles of aluminum. We do that by using the molar mass of aluminum, which you get from the periodic table, and that is 26.98 grams of aluminum in 1 mole of aluminum. So you could either carry out this first calculation and get an answer and then set up the second calculation, or you can do a run-on calculation, which I'm going to do up here just to show you the 2 different ways to do it. Once you have moles of aluminum, you can use the mole ratio from the balanced reaction to get to the substance that the question's asking us about, which is aluminum bromide. So if you look at the balanced reaction, 2 moles of aluminum give us 2 moles of aluminum bromide. All right. At this point, if we stopped, whoops, I should have written moles here, we would have moles of aluminum bromide. However, we actually need grams of aluminum bromide in order to calculate percent yield, or get theoretical yield is typically in grams. So I'm kind of running out of room here, but now we want to go from moles of aluminum bromide to grams of aluminum bromide. So we use the molar mass of aluminum bromide, which you need to calculate, and you would say that's 1 aluminum, and it has 3 bromines, and you add those molar masses up, and you get that the molar mass of aluminum bromide is 266.68. Oops, 1 mole goes in the bottom. Moles cancel. And the 266.68 goes in the top. When you carry out this entire calculation, and I would go ahead and do it on your calculator to make sure you're using your calculator correctly, you get that the theoretical yield is 59 grams of aluminum bromide. Okay, so the actual yield, as I said, is always given to you in the problem, and they said it was 50.3. The actual yield should always be less than the theoretical yield. Remember I said they're always competing reactions, or it doesn't go to completion? So your percent yield should always be less than 100. If it's more than 100, you probably did the calculation upside down. So to get percent yield, put the smaller number on top, actual yield on top, theoretical yield on bottom, multiply by 100, and in this case, the percent yield is 85%. I'm going to talk a bit more about limiting reactant now. Limiting reactant stoichiometry problems are considered by most to be one of the more difficult types of problems in chemistry. So it takes a lot of practice, and you're going to really need to be alert and listen now. So this is a conceptual question first, just to get the idea across. If we have, let me scooch that over, all right, 5 molecules of methane, CH4, and 8 molecules of oxygen, which is the limiting reactant, which one's going to run out first? At the bottom of the page is probably the most important thing to get out of this lecture. If you have a limiting reactant problem, and how will you know that? You will know that because it gives you quantities for both reactants, okay? Gives you quantities for both reactants. That tells you have a limiting reactant problem. And what you do when you have a limiting reactant problem is you have to figure out how much product each reactant will give you. So you need to do a stoichiometric calculation for each reactant. The reactant that gives you the least amount of product, and that's, you have to go through the whole stoichiometry thing, is the limiting reactant. The reactant that makes the least amount of product is the limiting reactant. So we're going to start with methane. We have 5, you can say moles or molecules, whatever. That coefficient can stand for either. Just has to be something you can count. So we have 5 molecules of methane, and we use our mole ratio anytime we want to go from one substance to another. And we can see that for every 1 methane we make, or we use, we make 1 carbon dioxide molecule. In other words, the mole ratio between methane and carbon dioxide is 1 to 1. So 5 moles or molecules of methane will make 5 moles or molecules of carbon dioxide. We do the same type of calculation for oxygen, and then we compare how much carbon dioxide each of these reactants can make. So looking at oxygen, start with 8 molecules or moles of oxygen. Here's the mole ratio of oxygen to the same product. You've got to compare them both to the same product. It doesn't matter which product you choose, but it needs to be the same for both reactants. So the mole ratio of oxygen to methane is 2 to 1. And so this calculation is 8 divided by 2, which means that we can make 4 carbon dioxide molecules if we start with 8 oxygen. So at the previous slide, let's see, so oxygen can make 4 CO2, and if all of our methane reacted, it could make 5 CO2. And so which of our reactants is limiting? The one that makes the least amount of product. That would be the oxygen as our limiting reactant. That means the other reactant is a reactant in excess. Which of these 2 reactants will determine how much products can actually be made? The limiting reactant is the determiner because it's going to run out. As soon as it runs out, no more product can be made. So you do the rest of your stoichiometry using the limiting reactant. That will give you the accurate amount of product that can be made with this reaction. Here's a more typical limiting reactant problem. Starting here. What mass, so grams of ammonia, ammonia, if you don't already know, that's NH3. That's another thing you need to commit to memory. It's a really, really common compound. What mass of NH3 can be produced if you have 100 grams of nitrogen and 500 grams of hydrogen? How do we know it's a limiting reactant problem? Because the problem gives us quantities for more than one reactant. So that's, again, each time you have a limiting reactant problem, it's 2 separate stoichiometry problems, one for each reactant. Don't make the mistake of saying to yourself in your head, oh, well, there's less nitrogen, doesn't that mean it's limiting? No, no, no. Because it also depends on the coefficients in the balanced reaction. So don't fall into that trap. And it also depends on the molar mass of each of these. So what I would suggest now is put the video on pause and try working this out on your own. You'll notice here that, here, let me divide these up. All right, so here is the calculations for the reactant of nitrogen. We had 100 grams of nitrogen. So the molar mass of nitrogen, remember nitrogen is a diatomic, so the molar mass of one nitrogen atom is 14.01 grams per mole, but you have to remember nitrogen is diatomic, so you have to multiply that by 2. So the moles of nitrogen that we have are 3.57 moles, and make sure that you take it all the way to product in order to determine the limiting reactant. You can't stop at the reactant moles. Using the mole ratio from the balanced reaction, 1 mole of nitrogen makes 2 moles of ammonia. So it's a 1 to 2 mole ratio, which means 100 grams of nitrogen can make 7.14 moles of ammonia. Do the same thing for the other reactant, which is hydrogen. Hydrogen is another diatomic, and just to remind you of the memory trick for remembering diatomics is Hofbrinkel. Okay, so H-O-F, Hof, B-R-I-N-C-L, Brinkel. That's just kind of a silly name to help you remember the 7 diatomics. And that's important because all of their molar masses will be double what's on the periodic table. So the molar mass of hydrogen, which is a diatomic, is around 2. So we have 247.5 moles of hydrogen, and the mole ratio of hydrogen to ammonia is 3 to 2, 3 to 2. So 247.5 times 2 equals, and then divided by 3, 165 moles of ammonia. So what's the limiting reactant here? Well, this nitrogen made the least amount of product by far, so the limiting reactant is nitrogen. And that means hydrogen is in excess. So to continue with our calculations to find yield, theoretical yield, we use only the limiting reactant. You may have noticed that I stopped at moles when I was finding the limiting reactant. I was basically kind of being lazy because as long as you get to moles, something to do with product, whether it's moles or grams, you can determine what the limiting reactant is. But to get yield, yield is virtually always in mass, grams. So looking back, nitrogen again is our limiting reactant. And we found on the previous slide that that could make 7.14 moles of ammonia. But to get to grams, we need to use a molar mass of ammonia, which is 17.04. And that tells us then that we can make 122 grams of ammonia from this limiting reactant. And again, as always, the calculated amount through stoichiometry is called the theoretical yield. This was a very typical limiting reactant problem, but you need to work quite a few of them because the wording will vary from problem to problem just to get some good practice.